When a golf ball hits a steel plate, it looks instantaneously, but if we slow it down, we see what really happens. The ball severely flattens against the surface. To calculate how objects interact, we first have to measure that deformation. If we take two perfectly aligned spheres and drop one onto the other, there is a moment where their geometric boundaries cross. The distance their boundaries overlap is called delta n. Physics engines treat this geometric overlap exactly like a compressed spring. The deeper the overlap, the harder the objects push apart. This outward push is called the normal force. Before we can figure out anything else in a simulation, we must calculate this exact depth of overlap. It tells us the baseline strength of the impact. That works for a dead center impact. But let's see what happens if we shift the bottom sphere exactly 0.25 meters to the side and drop the top sphere straight down again. Even though the top sphere is falling vertically, the normal direction of the push no longer points straight up. In physics, the normal axis is strictly defined by drawing a line connecting the exact centers of the two spheres. The incoming path of the falling object doesn't matter. The geometric offset between the centers entirely dictates the angle of the physical push. This is a diagram showing two colliding pool balls. Notice the dashed plane of contact separating them, and the distinct coordinate axes labeled n for normal and t for tangential. Because our normal axis is tilted, a perfectly vertical downward drop doesn't align with it. We have to mathematically split the falling velocity. One component pushes directly in along the normal axis, causing the overlap. The other component slides sideways along the tangential axis. As the surfaces slide against each other, microscopic friction acts like a second sideways spring gripping the contact patch. As the slide continues, this tangential spring stretches out, trying to stop the motion. But surfaces can't grip forever. There is a hard limit to how far this tangential spring can stretch. This limit is the Coulomb friction cap, calculated by multiplying the friction coefficient by our original normal force. Let's test this with actual numbers. Our normal force is 115.8 newtons. Our friction coefficient is 0.364. The sideways slide generated a trial tangential spring force of 71.55 newtons. Does the contact stick or slide? To find out, we multiply the friction coefficient by the normal force, getting a cap of 42.2 newtons. Since our trial force exceeds the cap, the object slides. The final friction force locks at exactly 42.2 newtons. Advanced contact mechanics requires this constant balancing act, calculating a growing tangential spring and checking it against a strict friction cap dictated by the normal force. Now we step back to the full simulation. By combining the outward push of the normal force and the sideways drag of the capped friction force, we generate a single resultant vector. This combined force dictates the top sphere's recoil path. The tangential friction pulls on the contact patch, forcing the ball to spin as it flies away. We can summarize this entire process in 3 steps. Step 1. Find the geometric overlap along the line of centers and use it to calculate the normal force. Step 2. Split the incoming velocity into components that align with that new tilted normal axis, isolating the sideways sliding motion. And step 3, stretch the tangential spring against the slide and apply the strict Coulomb friction limit based on your normal force. Locate the center line, split the velocity, and enforce the friction cap. Mastering this sequence gives you the exact blueprint used to code realistic collisions in professional physics engines.